All right, welcome back. Digital electronics. We're going to be going through an asynchronous counter today. So we're going to talk about, obviously, asynchronous counters, and we're going to define what the terms state and modulus mean. And we're going to go through a couple different counters using D flip-flops and JK flip-flops and understand what the ripple effect is because of those. Okay, so with an asynchronous counter, only the very first flip-flop, it doesn't matter if it's a D flip-flop or a JK flip-flop, that's going to be the flip-flop that's going to be using an external clock. Say, for instance, our breadboard companion, right? The little clock that goes up and down at the rising edge or the falling edge on that piece, okay? The rest of the flip-flops are going to be clocked by the preceding flip-flop's output. And we're going to choose either Q or Q bar, kind of depending on if we want an up or a down counter. All right, our asynchronous counters, they're slower than our synchronous counters because there's only one clock that goes into them, and the rest are all fed by the preceding flip-flop. There's a small delay in transaction there, or transition, so that we get what we call a ripple effect. All right, so small little pulses, because they don't all hit the rising edge at the same time, there's a delay. So that's the ripple effect. So that's why the asynchronous counters are slightly slower than the synchronous counters. And we're going to talk about the synchronous counters in a future lecture. So I want to talk about these states and the modulus for the flip-flops. So how do we determine, how many flip-flops are we going to need to do our count? Well, we got to pay attention to that. So our number of states is 2 to the number of flip-flops that we have. So the number of states that we're going to refer to is what we call the modulus. All right, the modulus is saying how many different counts we need to reach in this case. So if we take a look at this example here, we have a mod 12 counter. Okay, so that means that we're going to go from 000 to 1011. So we're going to go from 0 to 11, right? Because that's counting 12 digits. So in order for us to do that, if we use 2 to the 3, that's what? Only going to get us a count from 0 to 8. So we have to use a mod 12 counter because we have to use 2 to the 4 so we can get 16 states. Remember, 16 states allow us to count from 0 to 15, so that would be going 0, 0, 0, 0, all the way up to 1, 1, 1, 1. So we got to make sure that we choose enough flip-flops to make sure that we can cover all the states that we're counting. So we're going to use a 2 to the 4th or a 16 state. We need 4 flip-flops. We're only going to use 12 of those 16 states, though. And we're going to learn how to control, if we only want to count 0 to 12 or 0 to 11, right, versus making sure that it goes through all of them and goes 0 to 15. So we're able to put some limitations on there with some logic, so that doesn't happen. Well, let's just take a look at the basics here. If we have an asynchronous counter, all right, we have our external clock. All right, then we're going to be putting in our clock signal. So we're going to have our rising edge transition here. So this is the flip-flop we talked about before. This is a D flip-flop. And if we have one flip-flop, we're only doing 1 bit. So we're only able to toggle between 0 and 1. All right, so this is the 74 LS74. And in this scenario, right, remember Q follows D, because that's how we have this set up here. So every rising edge of the clock, Q will follow D. It doesn't matter what happens in between unless we hit preset or clear. But if we notice, preset and clear are connected to 5 volts here. So this clock is literally, what we're doing is kind of the divide by 2 counter that we talked about earlier in the year with this scenario here. So the output's going to be, take twice as long as the input. You can look at the graph here down below. So notice, for every 1 period of the clock, it's half a period of the output signal. All right, so remember that was the divide by 2 circuit. That's really what we're creating here. So the change will always take place on the rising edge of the clock when we do this. Now, when we add 2 flip-flops in series with one another, all right, well, this is going to be an up counter, and it's going to be 2 bits. So 2 bits will allow us what? That's 2 to the 2. All right, so any bits we're talking about, that's the exponent. So 2 to the 2. So it's going to allow us to count 4 digits. 0, 1, 2, 3. And then it's going to repeat. 0, 1, 2, 3. 0, 1, 2, 3. So that's what it's going to be doing. So we can look at every single rising edge of the clock here we're going to get two different outputs now. We have Q0 and Q1. Okay, what you need to notice on here is the very first flip-flop, the one that's attached to the clock. That's going to be our LSB, our least significant bit, because that's going to be the one that's constantly changing. Okay, the farthest flip-flop to the right, so in this case, it's Q1, that's going to be our MSB, our most significant bit. So it's very important that you understand the LSB and the MSB when you do this. So what this is going to clock through is 0001 1011. So we're going to do an up counter, and then it's going to cycle and start all back over. Okay, it's very important where you see how Q follows D on each flip-flop here. And you guys are going to do this one in lab so that you can see the outputs and how they go on and off, and how you'll see 0001 1011, and then it'll start back over. But it's always going to be hinged on, the first flip-flop's hinged on the rising edge of the clock. Okay, the second flip-flop, notice how the clock is coming out of Q bar and going into the clock of the next flip-flop. So the output Q bar is the clock for the next flip-flop. So every time Q bar changes between 1 and 0, okay, anytime it goes from 0 to 1, Q bar rises from 0 to 1, okay, that's the clock that's going into the next flip-flop there. Then if we want to do a 3-bit counter, right, that's 2 to the 3rd, which is 8. So that lets us count up to 8 digits. So we're going to be able to count 0 through 7, right? So it's going to go 0, 1, 2, 3, 4, 5, 6, 7. 0, 1, 2, 3, 4, 5, 6, 7. So it's going to repeat. Or, right, in binary, we're going to go 0, 0, 0 to 1, 1, 1. And that's what's going to flash on your screen here. Notice now, okay, the LSB, the least significant bit, is still Q0. Okay, it's going to be the flip-flop on the far left. The MSB now is the flip-flop all the way on the right, Q2. Okay, so that's our MSB, our most significant bit there. So you have to read these backwards if we're looking at this schematically. So if it's really going to go Q2, Q1, Q0, if we were to read this left to right, okay, because remember we want to read it as most significant bit to least significant bit, if we were to create a truth table and watch this go through all the different cycles here. So notice we're pulling the output Q on each flip-flop. Okay, that's going to be what our output is, so we're able to read that. And it's very important that you understand how we're going to read this, when we start driving our circuits and breadboarding and doing the counters here. It's going to be very, very, very important. Now, what I also want you to take a look at is, look, now there's two flip-flops that are using the preceding flip-flop's Q bar. So notice the flip-flop in the middle, the one that's tied to Q1, okay, it's getting its clock from Q bar of the first flip-flop. And notice the very last flip-flop, okay, the one that has Q2 associated to it. It's getting its clock from the output of the middle flip-flop's Q bar. So there's going to be kind of a double ripple effect here on this one as well. And we'll see kind of what the delay looks like. But this is how we're creating a counter. And if you still remember back to first semester when we looked at flip-flops, all right, the divide by 2 circuit, that's really what we're looking at. If you look here at the clock signal at the bottom, we have the clock signal, and everything's going to change on the rising edge of the clock. But we have the three different signals, right? We have our LSB, our least significant bit, Q0, and we have our MSB, our most significant bit, which is Q2. So if we look at those, each one, the period is dividing by 2. So notice, if we look at the clock signal, Q0, right? For every 2 clock signals, all right, or 2 clock periods, we get 1 period of Q0. Then for every, 2 clock, or every 2 periods of Q0, we get 1 period of Q1. And notice for every 2 periods of Q1, we get 1 period of Q2. So it keeps dividing in half. So if we add a 4th one on, it's going to get even slower, all right? But that's why it's our MSB, our most significant bit. That's the one that's going to move the slowest, and our least significant bit, our Q0, that's the one that's going to move the fastest. Okay, and this is why we have the ripple effect here, because there's a slight delay in propagation between each flip-flop that's in order. So the more flip-flops we have, the greater the ripple effect, because you can kind of see the delay, right? There's going to be a delay because it's not all the same rising edge of the clock. So as Q0 bar puts out, all right, there's going to be a slight delay, and that delay is going to kick into the middle flip-flop where Q2 or Q1 Q bar puts out a slight delay, and then our third flip-flop, Q bar 2, all right, is going to even have a larger delay before we get back to 0. And you'll actually see this as we kind of mess with the frequency and stuff doing our lab. You'll see where on your 7-segment display where there is a slight ripple effect that's going on because of the delay in signals, okay, as they propagate through all the flip-flops. And as we add more flip-flops in series, okay, we're going to have even more of a delay. All right, but here's where you can kind of see how this is impacted. So what's different about this one? This is a down counter now. So what are we going to do in this case? We're going to go 7, 6, 5, 4, 3, 2, 1. So what's the difference here with the down counter? All right, and we're going to get into this for both of them. But if we look at this one, now what's the input clock for the last two flip-flops? Okay, the first flip-flop still has a normal clock coming in. Okay, the next two flip-flops, they're still fed by the preceding flip-flop, but now instead of sending in Q bar, we're sending in Q. Okay, so Q1 or Q0, all right, that comes out of the first flip-flop is the clock for the second flip-flop. Okay, and then Q1, okay, is the clock for the second or the third flip-flop. So we're using Q for the down counter. If we remember the up counter, which we looked at earlier, we were pulling the clock for the next two flip-flops from Q bar of each of the preceding flip-flops. For this one, we're pulling from Q for the preceding flip-flops. So that's how we're going to do, a down counter. So if we're going to do a 60-second counter, we're going to be able to do up, or we're going to be able to do down when we do this. Okay, so how do we know how to do this? All right, if we want to have an up counter, we want to choose the clock input to be the opposite polarity. So we want to choose Q bar going into a normal clock. That's a rising edge clock, so that's the upper left display here where we have Q bar going into clock. And then if we still have an up counter, the upper right display here, or the upper right figure, we have Q going into a not clock or a falling edge clock. How do we know the difference between the two? The bubble in front. Remember, if we're inverting the clock signal there, we're going to hit the falling edge on that piece. It could still be rising edge, but we want to, if we have the opposite signal going in. So we have to make sure we have opposite polarities. And look at the down counter. Okay, if we want to go down counter and there's no bubble inverter on the clock, we're going to come out of Q. If there's a bubble inverter before the clock, we're going to come out of Q bar. Okay, so that's how we know the difference between if we're going to use an up counter or a down counter, what it looks like on our schematic. And it doesn't matter if we're going to use a JK flip-flop or a D flip-flop. The principles behind the up and down counter are the exact same for the clock. All right, so this is an up counter here, okay, for a JK flip-flop. And why is it coming out of Q? Because if you notice the JK flip-flop, each one of these flip-flops has an inverter before the clock signal. There's a little bubble. So that's why for this to be an up counter, we're not going to pull from Q bar. We have to pull from Q because it has to be the opposite polarity going into the next flip-flop. So that's how we're going to create an up counter using a JK flip-flop. And we have to remember what we learned about JK flip-flops with the truth table, right? What the different states meant. If we had 0, 0, 0, 1, 1, 0, and 1, 1, what that meant for our flip-flop, all right? Whether we would go to 1, go to 0, or toggle, okay, or stay the same. Okay, we have to look back at the truth table of how that works for our flip-flop. And notice the same principles still hold true. All right, it's a divide by 2 circuit because we are putting flip-flops in series here. So it really doesn't matter if we have a D flip-flop or a JK flip-flop. It's just how we're going to control, what's going in on each one of these. Okay, so notice how we're holding JK at 1. So you might want to look back and see, what does that mean for JK to be at 1 in its truth table? Does that mean we stay the same, or does that mean we toggle, or what? So remember that from a previous lecture when we've gone over JK flip-flops. Alright, 3-bit counter. This is a down counter now. So remember, we want to be, look at the polarity there. So we're going to use Q bar going into each one of these instead of Q, because there's an inverter on the JK flip-flop. The little bubble before the clock means we're inverting. Plus, remember, down counters have to have the same polarity. So Q naught is the same as the inverter. So down counters always have to have the same polarity. Up counters will have the opposite polarity as we go through this. And you guys are going to build these in multi-sim and work through them on the computer as well, so that you can kind of see the difference between your up counter and your down counter, and the difference between using a JK flip-flop or a D flip-flop. Alright, so here we have the modulus asynchronous counter. And why is it a modulus? Because we're controlling the count. Anytime we're using the fancy term modulus, it just means that we're going to control the count here when we do this. So we want the counter to go between 0 to 5. Okay, so we want to go 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5. And continually repeat as we do this. And we want to use an up counter. So we notice, okay, we're going to need 3 flip-flops to be able to go 0, 1, 2, 3, 4, 5. So we need a mod 6, okay, counter, which means what? We need to use a 3-bit counter, because we're going to have to go 0, 0, 0 up to 1, 1, 1, because that gives us 0 to 7. So we want to be able to count to 5 though, and you guys are going to do this, and you're going to breadboard this for me so that you really understand what's going on here. So in order to control the count, okay, this isn't too much different than what we've seen, except for now we're controlling when the reset or the clear happens. Okay, so notice all the presets go to 5 volts. Notice that since it's an up counter, we're feeding Q bar into each one of the Ds, but we're controlling the reset based on the outputs of the flip-flops, based on the Qs. So notice we have Q0, Q1, Q2. So this is where it's really important to understand the MSB and the LSB here. The MSB, the most significant bit, is Q2. The LSB, the least significant bit here, is Q1. So in order for us to reset this counter, alright, note in the upper left-hand corner, I have it written down, it says the upper limit of the count is 5, right? That's where we want the count to start over. We want to go 0, 1, 2, 3, 4, 5. We have to create a reset circuit. That's the NAND gate that you see on the screen, the 74LS10N. That's the NAND gate. In order for this to work, we have to do the count plus 1, and that's the signal that we send into the reset, the NAND gate. So notice we're going to send the number 6 into the NAND gate. The number 6 in binary, remember, is 110. And remember, you need to read this backwards, where Q2 is your MSB, Q1 is your LSB. So you're going to read this from right to left, being your value is left to right, if that makes sense. If you read it right to left, Q2 is 1, Q1 is 1, and Q0 is 0. How do I know it's 0? Because it's pulling from Q bar. We're assuming that the Qs are 1s and the Q bars are 0. That's going to get us to this state. So notice if I read Q2, Q1, Q0, it gives me 110. So I'm reading it right to left, but I'm speaking it left to right, because 110 equates to 6 in binary, and that's our reset. Because when we get to 6, we want to reset the counters, because we wanted to make sure it gets to 5. So 6 is our reset when we do this. So this is going to be very important for you to understand. But remember, you have to read MSB to LSB to do this. You cannot go the other way and say 1, 1, 0 looking at the outputs of the flip-flops. You'll get the wrong thing, because it really, if you're saying 1, 1, 0, it really means that it's coming out as 0, 1, 1, which means it's coming out as 3, not as 6. So you have to make sure that you're reading everything correctly, the outputs of the cues on the flip-flops. And I'll go through this a little bit more in class as well, so that you understand that the reset has to hit whenever the value gets to 6. So it's very, very important that you guys understand that piece. And we'll go through it in our labs. Alright, so if we want to do an asynchronous counter design, the first step is we want to choose our counter type. Are we going to be counting up, counting down? Okay, so then when that tells us the modulus that we're going to pick, right, how many states do we need to do? Then we want to select, do we want to do a JK or a D flip-flop? Okay, determine the number of flip-flops and determine the count limit. So I'm going to make you guys do some different counts. I might make you count, 2, 4, 6, 8, or I might make you count 0 to 5, or I might make it count 3 to 6, or different things like that. So I'll give you different challenges in class where you're going to have to do the schematic and all that for me as well. Alright guys, well that's the end of this lecture. Like I said, I'm going to go over a little bit more in class, a little bit more in depth, and I'll be interacting with you guys as you build your schematics and simulate your circuits and make sure everything's working good. So else guys, have a great day. I'll see you in class.